Good morning, sir.
Good morning. Let us start today. Today, we will start the discussion of strain in case of polar coordinates. First, we have to make it clear what is exactly the polar coordinates is. Now, we know almost all our discussions in this class, as well as in other cases, other subjects, we use the rectangular coordinates, which means we imagine there is one straight line along horizontally on your plane of paper, and this line is defined as x-axis, and another line which is vertical to this x-axis is defined as y-axis. And in case of three-dimensional uh, Cartesian coordinate system, and a third line which is vertical to both of them, which is defined as z-axis. And now, for any point somewhere, say here, any point somewhere here, and any point somewhere here, you see the distance of that point from y-axis, vertical distance, is defined as the x-coordinate. Distance of that point from y-axis, vertical distance, which is defined as y-coordinates, and distance of the point in the case of three-dimensional axis towards z-axis, uh, from 0 to z, with point of intersection of the vertical of this point on z-axis, and the distance from origin to the point of intersection is defined as z z coordinates itself. Now, besides this Cartesian coordinate is defined as Cartesian coordinate, we use another coordinates defined as polar coordinates. There we have taken into account we taken into account in x, y, and z coordinate system is Cartesian coordinate system. Uh, the linear dimensions, linear distance from of a respective point from three different axes. But rather than this relevant linear distance, we may have some other, I mean, the vectors are formation at our hand, and which we have to see how does it behaves. A particular point or particular set of matters, how does it behaves according to these coordinates. This coordinate is defined as arc theta coordinates, or or defined as polar coordinates of a point. Its arc theta coordinates means the point distance of the point from the origin. This is given as r, and the distance, if the point moves a certain distance, a certain radial distance, the angle between the initial and final distance is defined as theta. That is arc theta. These polar coordinates of a point in such case other than x, y, z is defined as arc theta coordinates. Means one one of the coordinates r is telling you the distance of the point from the origin. Origin means points of intersection, all three Cartesian coordinates. The distance of particular point from the origin, and if that point moves to a certain angle, a certain degree, anywhere left or clockwise or anti-clockwise, the in-between angle subtended by the straight line joining origin to this point is defined as the theta, or arc theta, or in terms of polar coordinates. So here we are coming into account the distance, direct distance, and of a point, and if the point moves anywhere from the over the plane of a piece of paper, what is the angle in between the initial and final position? So what we are supposed to do here, what we are going to do here is to use this conception in case of a particular body or space matter which has a certain size and dimension. Although all of them are infinitesimally small, you know what is the meaning of infinitesimally small, which is all has dimension which exist, but all the dimensions are almost near to the zero itself. It is the smallest among the smallest, but not exactly zero, not dimensionless. So the polar coordinates of point A, which is given here, let's rewrite the point is comparatively difficult here. This is the point A. This is the coordinates of the, this is the point A itself, and the radial of a point A is r and theta. What is theta here? This is r, radial distance from 0 to point A here. This distance is the r as per polar coordinates. And what is the distance theta here? The distance between this, the angle between this angle and x-axis itself. So you see, for polar coordinates, we are also using x and y axis at least, not z axis. So, and it is exactly two-dimensional coordinate system, exists in two-dimensional coordinate system, not in three-dimensional. So initially we have defined a point over the space in x and y axis, which definitely have x and y coordinates, and it has other two coordinates here. Here is distance as per polar coordinate. It has other two polar coordinates. One is the distance from A to the origin, that is r, and one is the angle subtended by the straight line from the from x-axis, that is equal to theta itself. These two are the polar coordinates. And now the radial and circumstantial displacement of the point is given as r and u theta. Radial and circumferential displacement of this point is defined as u and u theta. So if this point displaced to a certain distance, that will be termed as u like this here. And if this point displaced at any angle from the point A position, it will be defined as t theta u theta itself, like this. Now consider an elementary radial elements A, B, C, D as shown in the figure. What is this? A, B, C, and D. A, B, C, and D. This is a not a cube, but a more or less rectangular space. In elementary radial elements, it is considered elementary radial elements. So what we should see here, we have A, B, C, D. Why it is defined as radial elements? B has a certain radius. A has a certain radius which is equal to R. You can say by radius means if we subtend, if we make a circle of R, of with radius R, A will be one of its point. And so it is radius of the circle. Radial distance is another type. We can explain that it is a radius of a particular circle going through that particular point. So I am telling you again, the radial distance of a point over a xyz axis is the diameter of radius of that particular of a circle which goes through that particular point and whose origin at O. Okay. Next, so this is the elementary radial element. So this is A and this is D. It subtended an angle here. I will discuss it. That is theta 1 and theta 2. Next, that is B. It is on the same radial line. So it has the same radial same angle intended theta from x-axis. Next, it is the point C, which is on the line D and C, and it's also subtends an angle theta plus the distance of here. Now, what happened? And you know, the any displacement in radial direction is given as u r, and any displacement in the circumferential of this any circumferential displacement is given by u theta. So terms of radial displacement u r and circumferential displacement u theta. Now we have gone through ABCD. Now let point A, we have seen just a moment before that set coordinates r theta get displaced under deformation to A dash with coordinates r plus delta r. Say under the action of external forces over the body itself. Now the point A got displaced to point A dash here, this position. So it has what? This point should be defined by means of the distance of the radius from the origin, and this point should be defined by means of its angle with the x-axis itself, or the angle of the line joining origin to that point made with the x-axis. It will be the theta radial coordinates of it. So what will be the radial coordinate? R is A dash, so R is increased by delta theta, u theta, u r, and theta is increased by here given as alpha. This portion is going through the A dash here. This is A dash. If we draw this line from here to here, and this line will intend with this line passing through A by an angle alpha itself. So what is the polar coordinates of A dash is given as r plus u r theta plus alpha itself. So if we want to make a circle with radius r plus u r and with origin at O, we'll have the A point A dash with one of its point on its circumference itself, and it will circumscribe an arc of angle equal to theta plus alpha, where this theta plus alpha is the angle subtended by the line joining r plus u r to the x-axis itself. So this is a coordinated polar coordinates of A, and this is the polar coordinates of A dash after the deformation by the external shock, external force, etc. Next we got the neighboring point P. What is where it is here? What should be its radial distance? Radial distance already we have up to the point A is radial distance given by r. So we can say that up to the point A and B is equal to delta r, and the point B is equal to r plus delta r, and this line, it is on the same line from 0 to A. So the line from 0 to B intends the 0 to A, it is the same line over up to the 0 to A but extended up to B. So the line 0 to B, O to B subtending an angle with the x-axis, which is equal to r plus delta r for radial distance, and which is equal to theta itself, because it is on the same line through which the uh, straight line from O to A dash, O to A is plotted. So the polar coordinates will be of B r plus delta and entire theta, and polar coordinates of A is r plus theta, and the polar coordinates of A dash, or the position of A dash, with is r plus ur and theta plus alpha itself. Now this point P moves to B dash with coordinates like this. Say this point B here moves to the point B dash, so that A dash, B dash, C dash, D dash is our position of the say rectangular elements over the same space. So how will get the value of, how will you get the radial coordinates, polar coordinates of C dash? C dash moves, initially it was r plus delta s. It says the radial coordinates of radial distance of C dash originally. The radial distance of the point P originally.
Hello.
It goes to Hello, follow.
सर
हाँ,
सर इधर बारिश तेज हो रहा है सर, हम क्लास से बार बार निकल जा रहे हैं सर
22
नेटवर्क प्रॉब्लम से।
कहाँ हो ये, तुम लोग कहाँ है?
हम्म
22 তোমরা তো 2018 দেখাচ্ছে তো।
बाहर में।
ঠিক আছে, এখন there is no
सर
LMS today.
कल अटेंडेंस
There is no LMS today.
सर एलएमएस काम भी नहीं कर रहा है सर।
LMS नहीं
सर
चल
कल
रहा है,
अटेंडेंस छूट गया था सर।
LMS नहीं चल रहा है, तुम्हारा एड्रेस हम दीजिए।
सर तो अटेंडेंस का
I will take this from the screen. ठीक है, I will take the
Okay, sir.
यस सर
other alternative.
ओके सर।
At this I am taking this point, and at the end I will take another time. That's all.
कल का अटेंडेंस के बाद में बोला नहीं आपको इंग्लिश में।
ठीक है, I have taken once, and at the end I will take again. No. Where I was, yes. The point B here was r plus delta and theta. Now, the point B dash, initially what happened to B, this position only changed along the radius only, but along the angle with the x-axis, its position didn't change. But B dash has changed both of them. So how, what will be the coordinates of B dash? So r plus delta must be there, and you have see that any change along the radius is will be given by ur, and plus rate of change of ur in terms of in terms of radius multiplied by the change delta r itself. It is the radial distance or radial coordinate of B dash. Initially r plus delta r, then it added because the radius is changed along the length and beyond r. So this is delta 8 r plus ur. Displacement. The displacement of r is here, we are adding here, and the rate of change of ur with respect to r multiplied by the original length of the point B, that is dr, is added. Similarly, the angle angular coordinates was initially at the position B, it was theta only. Now it is added by an angle alpha, and rate of change of this angle alpha with respect to r multiplied by the rate of change of length again, that is delta r. So delta r is the change in length from A to B, and that we are using, that is for the making the coordinates. You see, we have at the point B is here, we are using here r plus delta r. Next, we are changing this delta rate of change of this delta r. Rate of change of what will be the change of this delta r in case of any displacement. So how will you know the change of delta r? We will first find out the rate of change of the length ur, or which is the displacement coordinate of the radius, and rate of change of our alpha, which is the angle made by the straight line passing through the D with the straight line passing through the A and B. So this is the rectangular coordinates. This is the rectangular coordinates of the point B dash. Now we have now got an idea what is the rectangular what is the polar coordinates of A, B, A dash, C dash, and A, B, C, D, and A, B, A dash, A, B dash, C dash, D dash. So what we have here, A, B, C, D, and after deformation becomes A, B dash, C dash, D dash, and we have defined the coordinates, polar coordinates of A and polar coordinates of B, and after it changed to the position, shifted to the position A dash due to deformation, we find out the polar coordinates of A dash as well as B dash. So far, we have not taken into care the polar coordinates of D and C itself. Now, the length A dash B dash. So what will be the distance? Length A dash B dash will be delta r plus delta ur by r into delta r itself. So length A dash B dash is the difference between the radial coordinates of A and B itself. Radial coordinates of B is this one, and radial that of A is this one. And if we uh, eliminate this portion from this portion is reduced to delta r here, and delta ur by delta r into delta r here itself. So length, one of the length A dash B dash is given as delta r plus delta ur by dr multiplied by delta r itself. So the length was the initially it was delta r plus delta ur by dr into delta r. So what we can do, if we want to know the strain, radial strain, means the rate of change of the length A dash B dash, rate of change of the length AB due to the external load, it will be given by this distance A dash B dash minus the original this length, that is the r, that is AR. This is the final length and this is the original length. Difference between the original and final length will be only dUr divided by dr into delta r, and the strain, the difference between the original and final strain divided by the original strain, this portion dUr by dr multiplied by dr divided by the dr itself, delta r itself. Delta r means it was the original distance between A and B. So the radial strain is become, this delta r will cancel each other, and delta ur by dr is equal to the radial strain, radial represented here itself. So we got the radial strain here. Next, we have to go to what will be the circumferential strain. What will be the circumferential strain? Epsilon theta. Epsilon theta is caused in two ways of the element ABCD. Undergoes a purely radial displacement, which undergoes a, if the elements A, B, C, D undergo purely radial displacement, there is no other angular change and movement due to the radial displacement, there are certain changes in the in between angle itself, but angle is not changing by its own without changing the radius itself. So with this assumption, the length AB is defined as r delta theta and changes to the circumferential length AB. Okay, what is this? This is the length AD itself. Just 1 second. Now, this length AB, initially it was r into delta theta itself, which is multiplied, uh, changes to r plus u1 into delta theta itself. The circumferential cell is caused in two ways. Just 1 second. The length AB, which is the circumferential length. Just 1 second, please. I am getting some confusion. Oh, that's right. This length, which is here A and D, not AB but AD, which is defined as r into theta. R is the radius and theta is the in between, r into delta theta, where r is the length of the wave and r is the distance of the point A from origin, and delta theta is the angle subtended by this small r. So this circumference is here. AD is the circumferential length in that r plus delta theta. And what will be the circumferential length at the point B? Just 1 minute. Now, the circumferential length AD changes to r plus UR into delta r itself. Here, we are increasing any change in radius with the distance r UR itself, which is the radial distance, but not delta r, which was originally the radial coordinates of B. We are saying that r plus UR into delta theta is the change in length, change in circumferential length of the particular element itself. So what happens? The strain due to radial movement alone is r plus delta theta, which is the r plus UR into delta theta minus r delta theta, which will raise r delta into delta theta itself. What is this? Which is become r delta r theta, UR delta theta full become. This is delta r. UR into delta theta divided by r delta theta, which is given here. Yeah. This is actually, this will be UR, not delta. UR into delta theta divided by r delta theta. So UR divided by r. This is the circumferential strain due to the radial movement along. In addition to the point D moves circumferentially to D dash through the distance, the point D next moves to D dash itself as it is reaches here. Point D here, it was there, but due to the movement of point A dash, D moves to D dash itself. So not only radially, but it is radially as well as the circumferentially it has a movement itself. So that we have to calculate in a different way. So the point P moves circumferential to dash to the distance equal to u theta. First, the distance was u theta plus rate of change of u theta due to the change of theta multiplied by delta theta itself. Originally, the subtended angle between these two positions was delta theta. So, not originally, but after its deform, the angle is angle at the origin deformation is equal to delta theta itself. So, u theta plus delta u theta by theta multiplied by delta theta. This is the circumferential length. Since a point A moves towards circumferentially through delta u theta itself, point A you can move radially as well as circumferentially. It moves by the amount u theta. Then the change in AD is dy here by d theta itself. dy d theta multiplied by, thus the circumferential evidence is moves circumferentially through u theta here. The change in there in AD is duy divided by d theta multiplied by delta theta itself, and the strain due to this point port is del uy by del theta r delta theta by delta r equal to 1 by r d2 square u theta by d theta itself. So the change is duy here. There is one change u plus r. The total circumferential strain is u plus r, which is originated from here. Due to radial movement, there is a change at the position of D, and as well as due to the angular movement or circumferential movement, that is the position is becomes d u theta r theta delta theta by r like this. So 1 by r d square d2 u theta divided by d theta itself, because these two theta is cancelling each other, and 1 by r d theta u theta 1 half d theta itself, which is not square, but actually this is not square, 1 by r d theta by du theta divided by theta itself. So it will reduce to ur by r plus 1 by r d theta by du theta itself. Now, to determine the shear strain, this is that circumferential strain ur by r 1 by r d theta u by d theta. Circumference due to the change in radial distance, change in the circumferential length. Now, to determine the shear strain, we have to move in the following way. The circumferential distance of A is equal to u theta, whereas that of B is u theta plus d u theta by dr into dr itself. The magnitude of a theta 1, this is not theta 1 but theta 2. The magnitude of theta 2 is u theta plus d u theta by dr into delta r itself. D u theta plus d u theta by delta r into d theta itself, minus a into r plus dr into 1 by r. But alpha is no u theta divided by r, u into theta divided by r. So if we replace alpha, what will happen? Here u theta divided by r into delta r, and we have here minus this minus du theta plus dr itself. minus du theta dr. Thus it becomes, this is cancelling each other. This is becomes du theta by dr minus du theta dr by r itself. Similarly, the radial displacement of this dx, just 1 second. The radial displacement with this of A, which is ux, whereas that of d is ur plus d ur by d theta into delta theta. Means ur is the length, ur is the displacement is supposed to be on the radius r, which is rate of change is multiplied by delta theta itself. So delta theta 1 by r d theta is ur plus dur by d theta into delta theta minus ur itself. So that's, this is cancelling each other, and this is also cancelling, theta is also cancelling each other, so it is become 1 by r dur by d theta itself. Hence the shear strain, hence the shear stress in r gamma r theta is equal to theta 1 plus theta 2 1 by r dr, this one and this one itself. So this is the, so far, the tensor analysis of the plane strain in the coordinate axis itself. Now let us start the compatibility equation to a certain extent. Initially we have seen that the displacement of a point, just 1 second, let me give the final A. Now let us do one compatibility. Let us start the beginning of the compatibility equation. We have seen that the displacement of a point in solid body can be represented by a displacement vector, that is, which has component ux, uy and uz itself. Ux is the cosine of the angle subtended by this displacement vector with the x-axis. Uy is the similar angle with subtended by the vector y-axis called cosine, and uz is the cosine of the similar angle subtended by the vector uz. Along these three axes, these are the distance of a point or coordinates of the point respectively itself. The distance of a point is specified by the 6. This is the displacement vector of the point, but displacement at a point is specified by strain components again. What is epsa xx, epsa yy, epsa zz, gamma xy, gamma yz, gamma zx. Epsa xx is the tensile strength along x-axis, normal to explain. Epsa yy, tensile strength along y-axis, normal to y plane, and epsa zz, tensile stress along of the z-axis, along normal to yz itself. Now, gamma xy is equal to, gamma xy is the stress acting over xy plane, and